Great. So we started studying curves, but by definition, these are one-dimensional, separable algebraic varieties. Okay. And the last time we proved a few preparatory results and also one important by itself result, namely for a local ring OCC of a point of a curve. Three properties. Are equivalent. First, that is smooth. In other words, dimension of the maximal ideal modulate squared equals 1. Second, that it is integrally closed. So geometrically, it's called normality. And third, that it is DVR. In particular, it implies that it's unique factorization domain.
Можно спросить?
Yes.
А вот что является, например, одномерным алгебраическим многообразием, но не сепарабельным?
That's the canonical example that is always drawn like this, sort of raviolo. So it's two copies of A1 glued along the punctured A1.
Спасибо.
Yeah, and today we will encounter this and other examples many times. So it was a very appropriate question. So it's inseparable. Curve. Well, according to our terminology, it's not a curve, but sorry, one-dimensional variety. Okay, so we'll need one more preparatory result, maybe the last one. And it says that one can go to the boundary along curves. So if say Ivan Matorin was to the invariant theory course last spring, then it's very similar to the Hilbert-Mumford criteria. But certainly it's much more elementary. So we have a variety X, U an open subset. There is a point also, and somehow you should imagine that this point is in the boundary, in the complement to U. And then the claim is that there is a morphism F from a smooth curve to X. Such that it does not miss altogether this open set. So the preimage of U is open dense. Well, it's enough to say that it's non-empty. Yeah, and by the way, maybe I should say that it's reducible from the very beginning. Okay, so it does not miss this open set, but on the other hand, this point in the boundary is also in the image. So you can somehow go from U to this small point X along a curve. Okay, so let's prove this. Well, again, it's a local question around this small point X, so we may assume our X affine, and then by the Noether normalization lemma, there is a finite morphism, well, finite and surjective morphism G from X to some affine space, and then the image of the boundary is a closed subvariety. Pardon me?
Почему оно замкнуто получается?
Because the finite morphism. Finite or else proper. So finite subvariety, say X, but it's strictly smaller than our affine space, and with set V is the complement. So it's an open subvariety in the affine space, and then just by definition, the preimage of this open V is contained in U, just by construction. And now inside the affine space, we have this V, and we have the image of a small point X. So take V in V and G of X, and in the affine space, we can easily connect them by a curve, namely by a line. Okay, take L, well, maybe a line L through V and G of X. Okay, and now we're almost done. So we produced a desired curve downstairs in the base, in the affine space. We have somehow to lift it back to X. Okay, but the lifting is very stupid. We just take the full preimage because it's a finite morphism. The full preimage will be a curve, and that's it. Let's take C prime maybe is the full preimage G inverse of this line. Okay, then the dimension of this C prime is definitely 1, right? Because it was a finite morphism. But still, this C prime theoretically could contain a zero-dimensional component, just points. Yeah, but it does not happen. So it's equidimensional. All the components of C prime are curves. since L is cut out, in the affine space by n-1 equations, and hence
сепарабельно. Почему каждый компонент сепарабельно получается?
Just no, we don't claim this. So we assume so far nothing about X, so we do not claim this so far. Okay, so C prime is cut out in X by n-1 equations, but each equation decreases dimension at most by 1, right? Hence, any component.
Владимирович, извините, пожалуйста.
Yes.
То есть, получается, C' это не кривая, потому что мы не требуем сепарабельности.
Yeah, I only claim that C prime is a one-dimensional variety. So any component of C prime has dimension exactly 1, or maybe I should say at least 1, but on the other hand, at most 1, so exactly 1. Okay, and now choose a component whatever, C tilde containing our small x. Okay, then this C tilde projects onto our line L by construction, and hence the intersection of C tilde with the preimage of our open subset is contained in C tilde intersect U. The open subset in capital X is dense in C tilde. Okay, and now finally take C is the normalization of C tilde in its ring of in its fraction field rational functions. Okay, and
Извините, а почему отображение сюрреактивное с C tilde в L?
Just by construction, it does not have any components that that are vertical, so to say, that project onto points. All the components project onto the whole of L.
Спасибо.
So we take this normalization, then we know that it is smooth. And this is it. This is what we wanted, right? We wanted to construct a smooth curve, and we're done. Okay, and so now back to separability questions. I will formulate a very important criterion how to solve if a variety is separable or not. It's called the evaluative criterion. Of separability. In terms of curves, namely, it goes as follows. So X, an algebraic variety. And I claim that it is separable if and only if any morphism from an open subset of a curve U of a smooth curve can be, well, how should I say it? If any morphism cannot be extended to the whole of C in two different ways. Okay, so this in this basic example we were recalled due to question of Sergei Aleshin like this. There are two morphisms. So there is one morphism from U, the punctured affine line. It lies in C, that is just the whole affine line, and there are two morphisms, the upper and the down extension, right? So there was one morphism G, but there are two morphisms G1 tilde and G2 tilde from A1 to this inseparable curve, right, to the radiol. So you see, this criterion works tautologically in this canonical example, but in fact, it works always. So in a sense, this example is universal, so to say. Okay, so let's prove this criterion. So, well, it's easy in both directions. So first, assume that X is separable, and assume that G1 and G2 are two extensions of the morphism G from an open subset of our curve to X. Okay, then we can consider a morphism, say, pi from our curve C to the square of X, namely pi of C is equal to the pair G1 of C, G2 of C. Okay, and then we know that on this open subset U, we land into the diagonal of X, right? Because G1 and G2 coincide with G over U. But then it means that since the diagonal is closed, it's just the definition of separability. The diagonal is closed. It means that pi of C also lies in the whole diagonal. But it means
Почему нам
that
потребовалась именно вот замкнутость, чтобы перейти от PU вложению дельта X к PC вложению дельта X? То есть чем мы воспользовались при этом переходе?
the diagonal is closed. We use the diagonal is closed. So C is the closure of U. So pi of C lies in the closure of pi of U. Right?
Спасибо.
okay, so it lies on the diagonal. In particular, it means that G1 of C equals G2 of C for any point. In other words, G1 equals G2. Okay, and we are done in this direction. Now, conversely, in the opposite direction, so assume that we have uniqueness. Of extension. And now let's consider the closure of diagonal delta x. Yes, so we do not assume that x is separable anymore. We are going to prove it. So we want to prove that the closure of diagonal coincides with the diagonal. The diagonal is closed, but a priori it cannot be. It could be bigger, but anyway, it's an open, a dense open subset. And let's take some point in here, x1, x2, and just by the lemma we started with today. By today's lemma, we can find morphism from a smooth curve, say pi, from a smooth curve to the closure of diagonal, such that this particular point x1, x2 is contained in the image, and also the pre-image of the open subset, the diagonal, is dense in our curve. Okay, and then
could you please explain why the diagonal is open?
Well, as always, I would say that this is a local question, right? And locally, it's very much open. It's even equal to its closure, right? I mean, all the affine varieties are separable, right? So if you cover your x by affine chart, then in any of these affine charts, the diagonal is open. It just coincides with its closure. Okay, but globally, as you know, it's not so. But okay. But by the way, you set a very very honorable example, and I'm very grateful to you because it's much easier for me to talk when I see somebody. So I have just seen Altan, and it helps me a lot. Thank you very much. Yeah, nice to see you. Okay, so where were we? Yeah, we were in the setting of this lemma, and for any curve of C. Oops, sorry. What did I do? What did I do? Oh, here we are. So for any point of our curve, we have the images. What did we? I forgot our notation. I had G. Yeah. So it's G1 of C, G2 of C. And we know that G1 restricted to this open set U is equal to G2 restricted to the open set U. And so by the uniqueness assumption, we must have G1 equals G2, and hence the image of the curve lies in the diagonal, and in particular, the point we start with, x1, x2, lies in the diagonal, and hence the diagonal is really closed. Okay, so I proved this evaluative criterion of separability, and this is really very useful. In the real life, this is the essentially the unique way to check separability of things. Now the next criterion is the evaluative criterion of properness. And it's very similar.
Sorry, I have a question.
Yes.
Yeah, so is there a classical interpretation of variation criterion?
And what do you mean by classical interpretation?
Like very intuitive understanding of this concept geometrically.
No, I think nothing can be more intuitive. I think it was given in most intuitive form. Now the criterion of properness is that a variety X is proper, and well, proper, that means its projection to a point is universally closed. Yes, if you change base, then still it's always closed. But somehow, but by definition, you first assume that X is separable. So it must be separable, and the projection to the point must be universally closed. So if and only if for any morphism, say G from U to X, from an open subset U and C of a smooth curve, this G extends, and then necessarily uniquely, because we assumed we assumed the separability and already proved this criterion to a morphism from the whole of C to X. Okay, so the separability is uniqueness, and properness is existence of extension. Okay, so in a sense, you say that your X does not have any extra limit points. Yeah, so you go along an open curve U inside X, and then you in principle you may tend to some point in the boundary which is out of X. If it does not happen, then X is proper, and you only have to check this for curves. Okay, like if you take the affine plane and puncture it at the origin, then you may find some, say, straight line passing through the origin, which will violate this evaluative criterion of proper at the origin.
So strangely, there is a geometrical interpretation for properness, but there is no separation. Is that right?
Well, we just had evaluative criterion of separability 10 minutes ago, and now we have a criterion of properness.
Oh, I'm asking about the like intuitive understanding of this concept. Like there is a intuitive understanding for properness, but there is no separation.
Well, probably you and me have different intuitions.
Okay.
Maybe that answers the question.
Okay.
Okay. So let's prove this. And again, in one direction, it's easy. Namely, assume that X is proper. And let's consider gamma, the closure of the graph of G. So the graph of G, it lies in U times X. Okay, and then the closure is taken in C times X. Okay, then it is a closed one-dimensional subvariety of C times X, and since X was assumed to be separable and C is also separable, and C times X is separable, then any closed subvariety is also separable. So in other words, it's a curve in our terminology. And now some of the plan is to prove that gamma projects isomorphically to C, and hence gamma is the graph of the desired morphism F. Okay, and
А почему F тогда будет уникальным? Ну, единственным.
no, the uniqueness already is known because we just proved the evaluative criterion of separability, right? We know that if X is separable, then the extension is at most unique. It does not necessarily exist, but it's at most unique. So we're only proving existence because the definition of properness includes separability. Okay, so want to prove that the projection is an isomorphism, and we know that this projection onto C is birational. It's a regional morphism, and it's an isomorphism over U, so it is birational. And the last lemma of the last class, last Thursday, then implies that this projection C is an isomorphism because we assumed that C is smooth, and we sorry, not quite an isomorphism. Maybe I should say it's an open embedding. If you recall the statement of this lemma, then any morphism from any curve to a smooth curve is necessarily an open embedding. Any birational morphism from any curve to a smooth curve is necessarily an open embedding. But the properness of X implies that the image of gamma is also closed, and hence this projection is an isomorphism. Okay, so we proved in one direction. now in the opposite direction. So we know the existence, and we want to prove that X is proper. And then we have to use the Chow lemma, or maybe even not the lemma itself, but one claim in the process of proof Chow lemma. So there is a projective variety Y and an open U inside Y, and the morphism from U to X, whose graph gamma H is closed in the product. Well, it lies in U times X, but it is closed in Y times X. Okay. Okay. So now take a point in this projective auxiliary variety, and take a morphism P from our curve to Y, such that this point lies in the image of our curve, and also the pre-image of this open subset is open dense in our curve. Okay, and we consider the composition from this open set in the curve C into X, and then let's take its extension. So by assumption, there is an extension. F from C to the whole of C to X. Okay, so V was an open subset in C, where we extended. Okay, and now we have a product morphism P and F. It's a morphism from C to the product of Y times X, and the image of C contains the graph of composition H composed with P on V. Okay. Okay, and in particular, the set of points P of C and F of C is contained in the graph of H. Okay, and in particular, the point Y is contained in the graph of H. Okay, and since Y is contained in the graph of H, it means and Y was any point in Y. You see, so it implies that this open subset in Y contains any point Y in Y, and hence this U just coincides with Y. Okay, and now we're almost done. So what we started with was a morphism H from Y to X. Okay, not from an open part of. So it was not partially defined, but regular morphism from a projective variety to X. Okay, and now what do we know? That X is the image. So now we know that X is the image of a projective variety. Y, well, in a separable variety X. Okay, then it implies that X is proper. Well, when we studied the notion of properness, it was one of the first basic claims that the image of a proper variety in a separable variety is necessarily proper itself. Okay. Okay.
And could you please just recall the statement of the Chau's lemma? Because I thought that we could apply it only to already proper.
It's not the Chau lemma itself. It's well, Chau lemma said that given a proper variety, which we don't know, you see, we don't know that X is proper, so we cannot apply Chau lemma. It's only a step in its proof. And well, if you go back to some November lectures, you will see this step there, and we're just reproducing it from there. Okay. So once again, X, we do not know that X is proper, so do not apply Chau lemma. But it was essentially a way to approximate every proper variety by a projective one. Okay. So there was a birational morphism from a projective variety to a proper one, and that's what you use in the construction.
So H is not an inclusion, but it's some. So for a proper variety, we would have that H is an embedding.
Yes. Yes.
But now H is not an embedding; it's just some morphism with closed graph. Okay, I got it. Thank you.
Okay, so we did prove the evaluative criteria. Okay, and now what I promised the last time is the some nice description of the category of smooth curves with finite morphisms. Okay, namely, well, so to say, the theorem about this says that this category is equivalent to the category, or maybe I should say not equivalent, but how to say, anti-equivalent, or the opposite. Well, I don't know. This category is equivalent to the category of fields capital K containing our base algebraically closed field K of transcendence degree 1. Okay, and one functor is immediate, namely a curve C goes to the field of rational functions on this curve. This is clear, and this is clearly contravariant functor, yeah, right? And in the opposite direction, given a field K, well, let me say, let me make a claim, and then I will prove it. But the claim is as follows: that as a set, this C is just the set of all discrete valuation rings inside K. Okay. And the topology is just Zariski topology. In this case, is the most stupid one. So all closed subsets are finite.
Почему нельзя вот взять спектр, например, просто?
The spectrum of the field K, first of all, this capital K is not algebraically closed, and it's strictly prohibited so far, right? Before we turn to schemes, we only consider algebraically closed fields. And also, whatever you do, the spectrum of a field is just one point. Yeah. So you want many maximal ideals, but there are no maximal ideals in a field. So you cannot just do this. So it's equal to the Zariski topology, and now the structure sheaf. O of open set U, and we already had this construction when we did normalization. Yeah, so we just do the same trick. It's the intersection over all U in capital U of the corresponding DVRs. Let's call it, say, R U. Okay. Inside this capital field K. So that's it. I didn't yet prove that it works, but I formulated the construction, and maybe let me continue. Maybe let me take this was 1. This was 1A. This was 1B, and another claim that any smooth curve S with the same field of fractions but now yeah, by the way, I'm sorry, when I formulated the theorem, I should say that this was not just smooth, but smooth projective curve. Otherwise, certainly there are many curves with the same field of fractions. Yeah, you just remove a point and the field of fractions stays the same, and that's the subject of the present point too. So any smooth curve with the same field of fractions is isomorphic to this field C of K that was constructed in the previous part of the theorem without finitely many points. Maybe I should say to an open subset C of k. Okay, so by C of k, I mean the projective, the smooth projective curve constructed in the first part of the theory. Okay, so this was maybe a little bit long formulation of the theorem, and well, I don't know your background, but I suppose that some of you have heard about Riemann surfaces, yeah, and the Riemann surfaces topologically. If our field K equals complex numbers, the curves, well, maybe the smooth projective curves are the same as Riemann surfaces. And there are some ramified covers of the projective line. There's just the Riemann sphere S2. Well, so they are unramified.
Значит, ramified.
Разветвленные. Unramified covers of S2 minus finitely many points. Okay, and then there is say Galois theory of unramified covers. Namely, the covers are the same as subgroups of the fundamental group of S2 minus this. Okay, and on the other hand, we have the field of transcendence degree 1, and they are finite extensions of the field of rational functions. This is the same as the field of rational functions on projective line. Okay, and there is the usual algebraic Galois theory of finite field extension of this rational field, field of rational functions on projective line, namely that such extensions correspond bijectively to subgroups, well, say finite index subgroups in the Galois group of this field. Okay, so these two theories are very parallel. Yeah, the topological theory that describes unramified covers in terms of finite index subgroups of the fundamental group, and the algebraic theory that describes the transcendence degree 1 fields, finite extensions of the field of rational functions as finite index subgroups in the Galois and the algebraic Galois group. Okay, these two theories are very parallel, and in a sense, this construction, this theorem I'm going to prove, establishes this equivalence directly. Okay, so our theorem is a way to see directly relation between algebraic and topological theory, Galois theory. So to speak. Okay, so now let's go to the proof. And we start with a remark that given a smooth curve S with the given field of fractions, we get a continuous map J from S into our curve C. Okay, just sending J of small point S is the local ring of this point, and this is a DVR inside the field of fractions. Okay, and this capital C curve or would-be curve set theoretically is just a set of all possible DVRs inside this capital K field, right? So in a sense, this is universal. This is the biggest such curve, but so far we only have a set structure in it. But at level of sets, any curve does produce a subset of this one. Well, if you wish, we had a lemma that the local ring at the maximal ideal defines the corresponding point uniquely, right? But in this case, for DVR, there is only one maximal ideal, so there is nothing else to reach.
Again, and the point, I mean, we take the localization, the local ring at point, at what point? Point C or at
sorry,
point?
sorry, yeah, sorry, you're right. You're right. It is a curve S, no, not C. Okay, and now let us produce an algebraic curve. Well, how to say it? Algebraic curve C, algebraic structure on the curve C. So, but I will not call it C. I will call it E. And then I will prove that somehow it is isomorphic to this C with the above structure. Yeah, because in the statement of the theorem here, we did equip our curve C with some structure Xi from the topology. We only don't know yet that it is a good thing, but we do have something. And then on the other hand, now for a proof, I will start with some algebraic curve. And it will play well in the end it will be this curve C, but I will produce it in some different form, so I will call it differently. An algebraic curve no, maybe let me write it down. E that will turn out to be isomorphic to C. Okay, so we know that our field K is a finite extension of the field of rational functions in some parameter T, but you see, there is no canonical choice of this parameter T. So here I'm making this choice, and this breaks somehow the invariance, the symmetry, the canonicity, and that's why I obtain something called E. So we make such a choice. T, and then it will give rise to projective line with coordinate T. Okay, and finally, this E, by definition, is the normalization of this projective line with coordinate T, in the field K. Okay, but we had this construction last time, as far as I remember, and now we're applying this general construction of normalization. So the main claim is that the natural embedding from E into C, just at the level of sets, is a homeomorphism and well, since the topology is a very stupid one, given by the closed subsets are finite, we only have to prove that it's a bijection.
А почему это неэффективно?
Just by our discussion, here in the beginning of the proof, right? Because C consists of all the DVRs, and now I consider only those DVRs that come from E. Okay, among all the possible DVRs inside the field K, I only take some particular ones that are contained. There are the local rings of E. Okay. So we only have to prove that it's bijection, and as we just discussed, only have to prove that it's surjection. Okay, so we take any DVR say called R. Well, that is contained in our field K, but contains the base field small k, and with a maximal ideal M inside R, and we want to prove that it comes from a point of our curve E, the normalization curve E. Okay, and let's prove this. So we have our parameter T, coordinate T, and you see, since we have this DVR and K, capital K, is this field of fractions, then for the parameter t, in fact, for any element of the field of fractions, there is that dichotomy. Either it lies in our R, or its inverse lies in our ring, in our DVR. But then just up to taking inverses, we may assume that it's T that lies in R, not its inverse. Okay, and then consider the integral closure, say B, of the ring of regular functions, just polynomials, in our field extension. Okay, and then we know that this integral closure lies inside our DVR. I mean, because well, we proved last time that DVR is integrally closed, or it's evident anyway, and T lies in the DVR, so certainly the whole integral closure does lie inside our DVR R. Okay, and now take the intersection of ideals. P is B intersected with the maximal ideal in R. Okay, so it's a prime ideal in our ring B, and clearly this prime ideal is not zero, because otherwise any element of B, well, not zero element is invertible. In R, right? Because the complement to the maximal ideal in R consists of invertible elements. So everything in B will be invertible in R, and hence R will be equal to K, which is nonsense. Okay, so P is really a non-zero prime ideal in B. Okay.
May I ask?
Yes.
Why did you use that T or T to the power -1 T inverse in R?
Because you know that the whole field K capital is the ring of fractions of R, but now the DVR how is the
and why is it so? Why can't R just be equal to K to lower K itself?
Well, okay, because, well, I don't know, it's probably problem of terminology, but in DVR you must have some uniformizer pi that is not invertible. In particular, it cannot be a field.
So I see, but still it's
and here not... maybe it's also due to embedding. Yeah.
But still it's not clear. Okay, come again. Why T or T inverses in R? Is it true that large K is
just because of this uniformizer? You see, any element of the DVR is some positive integral power of the uniformizer pi times a unit, right? And then in the field of fractions, any element is some integral power of this uniformizer pi times a unit.
Yeah, I understand. And how is large K the field of fractions of R?
Just, well, but it's transcendence degree 1, so there is no other choice. It must be field of fractions of any DVR inside it. Yeah, because transcendence degree 1.
Yeah, but it could be possibly maybe finite extensions of field of fractions?
Yeah, that's a good point. That's a good point. Yeah, maybe I should have said it from the very beginning. Where did I start? DVR. Yeah. DVR maybe R here, such that the fraction field of R is capital K. Yeah, sorry. I should have said it from the very beginning. We only consider such DVRs.
Okay, thank you then.
Yeah, I'm sorry. Yeah, it was a stupid omission on my part. Thank you
Следует
for...
текст о непрерывности прямого и обратного отображения.
Pardon me?
А непрерывность G и G минус первого откуда следует?
That's because the topology is a very stupid one. The closed sets are finite. So certainly, any map takes finite sets to finite. Yeah.
Спасибо.
Okay. Okay. So where were we?
Professor, another question here.
Yeah.
Because I don't see why R is equal to K then. I only see that all elements of B is invertible, so.
Yeah.
You also say B is a field?
Yes, but you see, K is certainly the field of fractions. K is the field of fractions of B, right? Because just by construction, B was the integral closure of something in this field of this capital K. So in particular, it means that the field of fractions of B must be K by definition.
Yeah, thank you.
Welcome. Okay, so now where were we? We know that B is the ring of functions on the open set U, where U is the pre-image of A1 inside P1 in E. I mean, we have this E was the normalization. So how was it? We had A1 inside P1. Now E was a finite cover of P1, and inside we have this finite cover of A1. Okay, that's the geometric picture, and hence our ideal P is the maximal ideal of some point E. Okay, well, maybe I should say E in this open set in E. Okay, and the localization of B at this maximal ideal is just nothing but the local ring at this point E, and it is inside our DVR R, but since EE was normalization and its local ring is smooth and DVR, it's DVR with the same field of fractions. Unfortunately, oh, maybe I can continue here. So this is a DVR with the same fraction field, and hence this DVR must be just equal to R. Okay, so we did prove the desired surjectivity. Okay, and now we can proceed. Though I'm out of time, unfortunately. So we produced an algebraic curve E with the same set of local rings as C. Okay, and this way we can equip C with an algebraic structure and in particular in this algebraic structure, the structure sheaf is just as we wanted. That is the intersection over all points in U of the corresponding local rings. Okay, I mean it's tautologically true for E, right? In fact, for any algebraic variety, it's tautologically true. And in particular, it's true for C. But since C was just defined in terms of all those DVRs, it's a canonical procedure, right? For E, we did need some choice of parameter T, right? But then what we produced with the help of this E is something canonically defined, and we don't need the choice of T anymore. Okay, so this is canonically defined, independent of the choice of the parameter. Okay, so we once again we did make such choice. We produced an algebraic curve E, and then we proved that this curve E is isomorphic. Well, it's bijective to the set of points of the curve C, and then we used the algebraic structure on E to transfer it to the curve C. But then the description of the resulting algebraic variety is independent of our choice of T. Okay, so it's kind of canonical construction.
And by the algebraic structure, you mean just a structure sheaf, or the cover by defining charts?
Yes. Well, once again, the charts are very stupid. The open subsets, by definition, are just the complements to finite subsets. Okay, this is very stupid. It does not distinguish between any two curves. Any two curves are uncountable or whatever, of the same cardinality as basic field K, and the topology is just finite sets or their complements. So it's nothing. The essential part is the structured sheaf, and here we have the structured sheaf, and it's canonically defined, dependent of.
Yeah, thank you.
Well, welcome, but unfortunately I was too slow, and well, unfortunately we have to stop here in the middle of the proof. Well, I'm sorry. I apologize for this. I will recall basic things next time, but we're essentially done. But I will say a few more words next time. Sorry. So I'm saving the notes for today. And if you have any questions, then please go ahead. So you, Mark and Altan, you are together, aren't you? Yeah.
Yes, we are.
Yes, great. Nice to see you both. But then now I'm stopping.
По первой теореме?
Yes.
Почему там эквиразмерная, получается, что G минус первая вот прообраза прямой, получается, от каждой компоненты имеет одну и ту же размерность?
Well, so on the one hand, it's the preimage under finite morphism. So the preimage has the same morphism as this straight line L, so the dimension 1, and it means it can have curves and points as components, right? Because of dimension 1. Now I claim that it cannot have points as components because there is the opposite estimate. The dimension must be at least 1, right? Because the straight line was cut out by n-1 equations in the affine space, and hence its preimage is also cut by n-1 equations in X. X was n-dimensional, so its dimension cannot be less than 1. So all the components have a dimension exactly 1, not less, not more, just 1.
Спасибо.
Welcome. Okay, so if there are no more questions, oh, yes, Wei Chen.
Yes, and would you please explain again why it's enough to show surjection from E to C?
Because it's an injection by, again, at the level of sets, it's injection just by definition. Because C consists of all possible DVRs, well, whose fraction field is K, capital K, right? And from E, we only get those that are local rings of its points. And in principle, there might be some DVRs not covered by this construction, but then I proved that all of them are. And if you want, okay.
Yes, thank you. And one more question is that how do we see that E is projective? Is a projective variety?
Just because it was normalization of projective line. So we started with projective line, and then took its normalization. So we know that the finite morphism, normalization is always a finite morphism. So you have a finite morphism to projective line, so it necessarily must be projective by itself, or maybe proper. But then next time I'll argue that it's projective.
Okay, thank you.
Proper. Okay.
Professor?
Yes. Yes.
Yeah, if you don't mind, can I ask about something I emailed to you?
Like what?
Yeah, about Gelfand's Gelfand's work.
Okay. Then everybody else, yeah, may leave. Yes. So certainly.
Sorry.
Yes.
Yeah. So, do you directly use Gelfand's results or Gelfand's work quotes for your
Me
paper?
personally.
Yeah.
Oh, yes, certainly I do. Yes.
Oh, I
Yes.
see. Oh, wait, because of the relation with representation theory.
Oh, yes, certainly. Yeah.
I see.
Well, he has a very, very basic result in representation theory that nobody can avoid. So everybody must use Gelfand's basic results.
Oh, I see.
Like there is very basic Gelfand trick for proof of commutativity of some Hecker algebras or some classification of principal series representations. So it's unavoidable. Everybody has to use his basic results.
There are some stupid things, but like, as I said, I bought the book, which is about lecture of hypergeometric series of Gelfand, which has done in Kyoto. But like, I thought, like, is there any other corrected work of Gelfand on hypergeometric series in any language, English or Russian, might be.
But well, again, there is a 3-volume edition of his collected works. It has a lot of works on hypergeometric functions. I don't know its relation with your book, if anyone is more complete than the other, but there is this canonical 3-volume edition.
Yeah, my book is very thin, so like there should be much better version.
Okay, yeah. Then so just have a look at this 3-volume collected works.
Is that in English?
Oh yes, certainly. Yes.
Okay. Thank you. Sorry.
Welcome. Okay, so see you Thursday. Goodbye to everybody.
До свидания.
До свидания.